the domain. So you have some function f, so it could be something like that, right? Then you're basically interested in the area under this curve. Let's say. Of course, the integral, the more general integral, can go downstairs and come upstairs again, and then you usually think of this as negative area. Okay, but for us, we'll only be interested in functions that are either 0 or greater than 0. So it'll just be area under the curve. And the way you do this in the standard way is called Riemann way. Is you basically split the domain into lots of little pieces, okay? And then you evaluate the integral's value at the midpoint. So you say this is, this is the height f at this point, x1. Let's say it's the midpoint, this is the x2, and so on. And this is basically f of x1, right? So then all you do is you take the width of x1, okay, how wide this is, and then you basically multiply the height by the width, so you basically get this rectangle, right? And then you basically do this over and over, right, for every piece. So this is essentially a midpoint rectangle approximation of the curve, right, the area under the curve. It won't be perfect, but it's a start. And then the idea is to basically, if you have n points, you do this, get n rectangles and sum their area up. But if you keep increasing n, you can get smaller and smaller slivers, and your rectangles, the sum of the rectangle areas will approximate the area under the curve nicely. So yeah, this is basically what I'm talking about. The definite integral is going from some place A to some real numbers to A to B. And yeah, so okay, let's there should be some. So what I just explained to you is a Riemann sum, and there's another one called the Day integral, but it's kind of the same, except instead of chopping the domain out here, this. So you just basically break it into pieces. This is square root of x, and then if your slabs are really coarse, you get this yellow sum of areas, and if it's very fine, you'll get the green one. And then the idea is now to let the number of rectangles approach infinity, in a countable way, and then you look at the sum of these rectangles as a limit. Okay. I don't want to get into limits now, but okay, so that's the intuition. Yeah, so the other main thing is it doesn't really matter for this course, but kind of pretty much at the beginning of modern mathematics, if you understand this other notion of an integral called the Day integral, right? So what we just talked about is the Riemann integral. As you can see, it's better and better. And Lebesgue integral is another sort of idea. So there you basically, instead of chopping up the domain regularly, you basically look at the height upstairs. Then you chop. Maybe you start with some big number here, and then you chop this into pieces this way. And then what you're interested in is a bit higher. So then you're interested in finding the set of all x whose f of x value is in this range, basically, right? So that means you pull out, say, this part. So this will be, the set of all x values in the domain that overlaps with this. Things get interesting here already, right? So if I ask what is the set of all x that maps f of x values in this range, then you see it's this part. So it's this one. Yeah, now we don't have this grid anymore. Okay, so in the Lebesgue world. So, and then, but also this part, right? So this part, this part. So you get unions of intervals downstairs for every interval range upstairs, right? You take the the range, chop it up, and then look at the inverse images downstairs. And then you construct the integral this way, right? So you basically multiply the height by the area of all these unions of intervals in the inverse image. That's the Lebesgue integral, and so it's more general. It's got a lot of properties, and what's really happening in we don't want to get too much into it, but that's essentially how you mechanically understand the integral. Now, the other main concept is these are like saying integral from a to b of f of x dx, right? That's this area of the curve thing. But sometimes you don't put this, right? So maybe you say something like this, minus infinity to, well, let's say I'm going to use lowercase x, and I'll use y dy, just because I don't want them to be the same variables. So now I can think of my horizontal axis as the lowercase y-axis, and I'm now interested in some integral. Maybe it keeps going like some density, it keeps going like this, and all the way to minus infinity. So when you allow one of these endpoints to approach negative infinity or positive infinity, then you're starting to talk about what are called indefinite integrals. And then the way you define an indefinite integral is no biggie. It's the same idea. You chop the domain like crazy, except instead of going to negative infinity directly, you say I go to some really large negative number minus m. Okay, and once it's minus m, it's a fixed number, so you still have the definition of the definite integral well defined, right? So then you find out what it is, and then you slowly let minus m approach infinity. So it'll be like a double limit. And then, for the full integral, which you don't put anything, it's just this integral sign. That means you have to let minus m approach infinity and positive m be the same number. Approach positive infinity for upstairs and downstairs. So then again, you have this double limit. Is that okay, Dimitri? Well, okay, something. Yeah, I mean, I'm kind of giving you in 5 minutes, like fairly advanced stuff, right? I mean, you have to really take math courses to really understand it. But for us, this is enough to kind of keep going. Yeah. So what is the main point for us? We have this. So we have this density lowercase f, okay, which is going to tell us, which is going to encode this probability. It's going to tell us that the probability that the random variable x takes a value strictly greater than a and less than or equal to b is given by this integral of the density function. And that's nothing but this, right? F of b minus f of a tells us everything to the left of b, the probability to the left of b. And f of a tells us the probability to the left of a, and a is to the left of b, right, less than b. So if you just subtract the capital F's, you get the probability. This is just the definition of f of a pretty much. But then this is the slightly new part, right? So this is the definite integral of the density function, probability density function, lowercase f. And why do we need that? We need that because our random variables in the continuum, it's hard to pin them down, right? If I pull my hair and measure how long it is, and it's my measurement, I randomly pluck hair from people and just look at the measurement. Okay, I'll have a scale, right? Up to my resolution of the scale, I'll know it's whatever number. But it's, but you can't really talk about, it just keeps going all the way down, right? Khan Academy has a really nice video. I recommend watching that one. Actually, yeah, that's the reference to the video. The video is Khan Academy's video on rain falling on some mountain, actually. Yeah, the basic idea is because we cannot exactly pinpoint what it is, we really only know it up to some tiny little epsilon around it. So the way you think about probability of a continuous random variable x taking a little value lowercase x is really by multiplying the density f of x at that point, and then you usually inflate it by some delta epsilon or delta whatever. Okay, some tiny width. That's the interpretation. And of course, if you cannot measure it, if your scale is really fat and you only have like, I don't know, whatever, centimeters, and you can't see anything finer, then you'll say, oh, my hair is between this many centimeters and that many centimeters. And that's okay, because then you can say, the probability that this hair plucking experiments end up in a hair length in some centimeter interval is given by the integral of the density function if you have one. So that's the idea. Actually, an even better example is if you want to just measure the rainfall that falls in a funnel, right? And then you have a graduated cylinder in the bottom, right? And in fact, India has some of the best rainfall measurements in the world since like 200 and some years of British measurements. Like every square mile or something, there's still a weather station, a manned weather station. And so anyway, that's what they do, right? They have this big funnel, this certain diameter, and then it's a graduated cylinder, and then you look at the lower meniscus and see where it is, right? And then that eyeballing is natural for continuous random variables because this is atoms of water, or molecules of water. Okay, that's that, and this is just the fundamental theorem of calculus. If we differentiate the distribution function with the integral, you get the density back. So, of course, the density f has to satisfy this condition, right? This is just saying something happens, because the probability of the entire sample space should be 1. And the probability of the entire sample space is the same as the random variable x taking any real value. So if we integrate it over the whole line, it should be 1. Okay. Yeah, so I don't know what this is. I won't play this, but I just want to see if it works.
In the last video, I introduced you to the notion of a probability. Well, really, we started with the random variable and we moved on to two types of random variables. You had discrete.
All right.
Discrete that took on.
Okay. He's saying this a bit slower, right? Okay, then let's move on. So this is our fundamental random variable, and down the road we will see how we can use the uniform 0-1 random variable to obtain any other random variable. So the uniform 0-1 random variable simply takes continuous values in the unit interval. Okay? So I have my unit interval 0-1, and and this random variable, if I take any interval here of a given width and slide it around, right, then the probability that my random variable will fall in that interval is the same, right? It's just given by the width of the interval. So that's what that guy is. And then you can think of it as this is how you write the density function explicitly. You'll say it's an indicator function of x taking the value in the interval. So that's by definition is 1 if x is inside 0 and 1, and 0 otherwise. Okay, so and then the distribution function of the random variable is simply coming from this definition. So we integrate all the way from -infinity up to x, right? And then the density. And so that's easy because to the left of 0 it's 0, so it'll take the value 0 if x is less than 0. And between 0 and 1, we're integrating like this. So we're integrating a constant function. So the area under this rectangle as we move just increases linearly, right? That's all that's going on here. So it's equal to x itself, and if it's greater than 1, it's going to remain at 1 here. It's 0. Now here's the other important thing, so you can ask, what is the inverse of the distribution function of this random variable? So the distribution function goes from 0 to 1. So for any x, it gives me back x. And the inverse also does the same, right? So this is what makes this an elementary random variable. So the inverse distribution function, that means I go from a point here back downstairs. The inverse is also the same as the distribution function, right? Because it's the identity map on the unit interval. And that basically is what drives this to be kind of the soul of every, well, the thing from which you can get any other non-uniform random variable. Okay, so it's called the fundamental model. Yeah, if you're uncomfortable with it, maybe I should say, because I don't really believe in the continuum. So that's why I like to do rigorous numerics. So you don't need to compromise here, right? You can actually, equivalently, you have this other random variable, which is the same as this guy, right? So you guys remember where the eraser was? So you guys remember the argument that gave the counterexample to the claim that the points in the unit interval, the real numbers in the unit interval, are countably infinite? You guys remember that argument? Okay. You guys remember countably infinite? What is the definition? Well, I know some of you don't for sure.
It's mapping from the natural numbers to, yeah.
Exactly, yeah. It's a mapping, right? That gives you essentially an index for every element. So it's a mapping, and we saw that the integers are countable because you can just loop around, spiral, and then rational numbers are also, right? Because you can spiral around. But then were real numbers in the unit interval countable? We said no, because what do? We made this. Is this Cantor's argument, or is it one that's okay? So, and remember, the counterexample Cantor gave was that basically he goes for any real number. He looks at the binary expansion. So, did it fall to the left or right? Right. So, if it falls to the left, it's 0. If it falls to the right, it's 1. Right. So, you can just think of it as a tree, basically telling you where it's going. So it will be some sequence of numbers, whatever, right? And then we said if it were countable, there is a whole list of them, and then I can create one that's never in the list by flipping the bits of the diagonal, right? Okay. So basically, you can use that to get the fundamental model as well, right? So to produce a point uniformly at random on the unit interval, what could you do if you just had a fair coin? So Bernoulli, 1/2, again and again, right? So product experiment. Okay. If you can flip a fair coin infinitely often, then this is essentially equivalent to producing a uniform number. Uniform 0 random variable. Do you guys see why they're the same? So think about how will I get a binary representation of a real number in the unit interval. Right? It's just a sequence of zeros and ones, right? Maybe it's here, and then maybe this side, and here, and so on, whichever one, right? So you have to somehow produce this infinite sequence conceptually, right? So that it's so the likelihood of producing one of these infinite sequences is the same for no matter. So if you catch a whole bunch of these sequences and put them all the ones that fall in this interval and all the ones that fall in some other interval of the same width, they should have equal probability of occurrence, right? So how will you do that with just fair coin tosses? Say I toss the coin. I can just paint the coin to be 0 and 1, right? Heads and tail, tail and head. So I can just look at the what landed, right? I can say, oh, first was a tail, one head, tail, tail, head, head, whatever. So I can just do this, right? If I have a perfectly fair coin, I'm producing a real number in the unit interval uniformly at random. So they're equivalent, right? So you don't need to buy into the existence of the continuum, right, to do probability. Okay, so this is just a generalization of the uniform 0, 1 random variable. So we have f of x as the indicator function, now AB, and it's exactly the same. And the picture is something like this. The density is going to be 1 over b minus a because the rectangle area should sum to 1. And then it will just grow linearly, right? And the slope, I mean, it's going to grow linearly like 1 over b minus a. Okay, so that's already a 2-parameter family of random variables. And I think this is how you sort of black box simulate it. If you say uniform minus 1, 1 in sage math, it'll give you samples. So if we try again, it's going to give you some other number between minus 1 and 1. So we'll get into a bit more on what's under the hood soon. So now the next main concept is expectations, right? So these are, so what do mathematicians do for a living? They basically take words in some natural language and just pervert it. I mean, beautify it, right? I mean, it's powerful because, you know, I like mathematics because, you know, you can do your poem, you know, or whatever, theorem, proposition, whatever, in a way where there's no room for misunderstanding, right? You completely get it or you don't. Tilo disagrees, but that's fine. I mean, yeah, if you know what you're saying and you know you have an axiomatic system, then it's there is no room for misunderstanding, and that's powerful. But again, it comes with its own drawbacks because you know expectation of x is you know is defined like this. It's called the population mean. So you take so it's called capital E of x. So now you integrate x with the differential of the distribution function. So this is just common notation to talk about both discrete and continuous random variables at the same time. You know, so this just means if it's continuous, then integrate x multiplied by the density. If it's discrete, then just take x multiplied by the probability mass function f of x and sum over all x values. That's expectation of the random variable or population mean. So we can define expectation of a function g of a random variable. So it's called e of g of x. And it's exactly the same. So instead of putting x here, you put g of x and do the same. So, of course, you know, you have to make sure that the integral itself is well defined. So this is to say that the expectation exists. So yeah, so you want to make sure that the integral of the absolute value of g of x, you know, integrated against the distribution function is finite. Okay, so then now basically the usual expectation of the random variable x is nothing but the expectation of the function g when g of x is x itself. So that's okay. So now think about this function. So g of x, right? So g of x. Oh, this is a typo. This should be expectation of capital X. Sorry about this. So this should be capital X. Okay, so think of this. G of x is now x minus the population mean squared. So what is that? That function g? It's measuring some kind of a squared deviation from the expectation, right? It's some kind of measure of spread, right? Quadratic, a measure of spread. So that's called the variance. So when g is this function, it's the expectation of g is called the variance of the random variable x. And that's because it's so common, it has a special symbol b for it. Right? So b of x is simply the expectation of x minus e of x squared, and that just means it's the integral with g as that function. And then there's another special thing called standard deviation, which is denoted by sigma of the random variable x, and this is simply the square root of the variance of x. So do you guys see that these things are actually outputs of integrals? They are themselves real numbers, right? They are deterministic. So so for a fixed random variable, the population mean is a real number, although the random variable will take different realizations. The same with variance. And then this again is another thing called the kth moment. So you're interested in g of x being x to the k. So so here are some properties of expectations. This just follows from properties of integrals, basically, and sums. So if the kth moment exists, and if j is less than k, then the jth moment exists. That's because this is what it means, or the kth moment exists. Won't be. And then if we have n random variables, x1 through xn, and a constants, a1 through an, then the expectation of the sum of ai times xi is just the sum of ai times the expectation of xi. Which just means you can take the expectation inside a weighted sum. Right? This is just because this is how integration works. And then if you have n random variables that are independent, then the expectation of the product of the random variables is the product of the expectations. Okay? So this is only true for independent random variables. And the variance of x is given by the expectation of x squared minus expectation of x the whole square. Oh, that's a typo. That should just be a separate bullet point. Sorry. Yeah, it's tired sometimes. You see, that's nothing to do with the independence. Okay. So this is a good exercise for you to try, right? So you should start with a definition of variance and show that when you complete the square, you get this out. So it's like a couple of lines of basic mechanics. So if a and b are constants, then the variance of a times x plus b is a squared times variance of x. So that's shouldn't be too hard either, right? Because variance will go into each term. We know this. So, but the variance of a constant b, right? What is the variance of a? Is constant b a random variable? No? Why not? For example, right? No matter what happens, all I will say is 1, 1, 1, 1, or whatever. 843, right? I'm the random variable. I just spit just one number at you. Right? I mean, why can't I do that? It's boring. So every time you do the experiment, you get the same outcome. But that's still well defined, right? Yeah, you'll have a distribution function. No, this is very important, right? This is very important. So if you have something going on, and then I have my random variable x, and this one always tells me, let's choose 17. It's just the 17 thing. It always tells 17 to me. So, well, what is its distribution function? This is definitely a real valued random variable. I mean, doesn't matter what the sigma algebra is, always spit this at me. So then the distribution function is going to be what? So what is going to be, so what is the probability of, so if lowercase x is something less than 17, will there be any events falling there? Because everything is going to just fall here, right? Nothing will ever happen here. So the probability will be 0 for any value less than 17, right? So it'll be 0, and then at 17, I punch a little hole, and then boom, I jump to 1, right? And it'll remain there forever. So you can think of, naturally, you can think of deterministic numbers. It won't make probabilistic sense all the time, but you can think of them as point valued random variables, point mass random variables, right? In fact, we will think of them this way to understand convergence of random variables, because we will understand limits of deterministic sequences in this sense, and then the random ones will make more sense. Okay, so the variance of B will be 0 because, because its population mean is B itself, right? So when I take B minus B, the whole squared, and integrate over the only value it takes, which is B, it's 0. So that's why that's there. But then the A part, which is a multiplicative factor, blows as a square. Okay, so this is so yeah, that means, when you just multiply a random variable by something, say bigger than 1, the variance is going to increase, a lot more. Okay, and then this property basically says if x1 through xn are independent and a1 through an are constants, then the variance of the weighted average is the sum of the ai squared times v of xi. It's just the finite version of that one. Okay, so these videos are good if you want a bit more slower explanation. So let's look at the population and mean and variance of the Bernoulli theta random variable, right? So let's, we already looked at this, f of x, and I said we put a semicolon next to before the parameter whenever a random variable is from a parametric family. We use the semicolon to distinguish that this is the parameter and this is the realization. So we already looked at this. It's simply theta if x is 1, 1 minus theta if x is 0, and 0 otherwise. That's the density of the mass function. And then here's the distribution function. Okay, so let's just recall. So let's just mechanically march through what's the first moment. So expectation of x, well, because this is discrete, I just have to sum over the two values, right? 0 and 1. So x multiplied by f of x. For 0 and 1, and when it's 0, it's 1 minus theta, it's 1, it's theta, so I just get theta. So the expectation of a Bernoulli theta random variable is theta. All the second moment argument is the same, 0 squared and 1 squared remains 0 and 1, so expectation of x squared is also theta, second moment. What is the variance? Variance is just the expectation of x squared minus expectation of x the whole squared, so that is now theta minus theta squared. So this is theta times 1 minus theta. So this is a nice, beautiful thing. So it's the heart of a lot of interesting dynamics, logistic maps, and so on. Okay, so what we also do is, especially when we get into inference section, we will use this kind of notation. It's common. So we subscript the expectation by theta to say that there is this parameter that the random variable distribution is, depends on. So we say E sub theta of x is theta, and V sub theta of x is theta times 1 minus theta. So this is just to, yeah. So here is just a little function in Sage Math, and then we can just, so all I'm doing here is just defining a function, theta, it just returns theta, theta returns theta times 1 minus theta. And I'm going to assume the user is going to only put values inside the unit interval, just for illustration. So here comes your sort of first heavy-duty user list comprehension. And let me, this is as good time as any, let me introduce you to points. P-O-I-N-T-S. So points, it returns either a 2-dimensional or 3-dimensional point, or sum of points. Sum means now aggregation. So yeah, so it's actually a basic geometric object. Okay, it's a graphics object consisting of one graphics primitive. So throughout, we will be using graphics primitive and compose graphics primitive to make plots. We will not use too much built-in magic. Okay. Yeah, so that's basically points. It can just, it's all you really need to understand some numbers in pictures. Okay, so what I'm doing here is I have this Bernoulli pop mean. Okay, so I'm basically rolling out numbers between 0 and 100. Okay, and then, so that's my list comprehension. My list is just from 0 to 99. But then I want my values to be between 0 and 1, so I just multiply it by 1 over 100. Okay, so now I have numbers between 0 and 1. And here I have a tuple in my list comprehension. So I have my x times 0.1 as the first element of the tuple, and the Bernoulli mean of x times 0.1 is the second element of my tuple. So I'm basically going to get points that come out at me in blue, RGB color blue, or RGB color red. You can dig more into other options there. That's all I'm doing there. So I'm just seeing that the population mean is just theta. So when theta is between 0 and 1, whatever it is, that's the mean. And this is the quadratic, theta times 1 minus theta. So here is the question: what Bernoulli random variable, what should theta be for this random variable to have the most variance? 0.5. Yeah, 0.5, right? Which is also here, right? I mean, it's, yeah. The fair coin toss has the most variance, as you can imagine, right? Okay, population mean and variance of the uniform 0-1 random variable. This is the other thing we'll slightly march through mechanically because it's continuous, but it's exactly the same idea, except now instead of evaluating the expectation for the discrete thing, yeah?
Sorry, just one question regarding the code before.
Yeah.
So why do we write for the variance P plus equals points? In the second, third line?
You mean this one?
Second line.
Oh, okay.
So that you do.
Yes, sorry, so did I do something wrong?
No, it's just a question why you need to say, so you say P equals points blah blah blah, and then you say P plus equals points.
Oh, wait, sorry, yeah, thanks. No, good. Please ask. So, because I'm aggregating it, okay, let's do this way. Sorry, actually, that's good. Yeah. If I just do that, I comment it out, all I get is the first plot, P. So
Yeah.
P is basically a graphics primitive composition, right? It just takes all these points and composes it inside. But then I want to overlay that with the red one.
Okay.
Yeah.
I think you could have written P equals P plus points as well, right?
P equals, yeah, I could have done that. Yeah. I don't know, actually. Yeah, probably. Yeah. Yeah, it's the same, but I like mine better because it's less keystrokes. So we will do this a lot. I mean, I hope we get to this. I have this simulation of a drunken drunkard walk in Manhattan. And the assignment is actually to do the drunkard walk in Manhattan in the future, where the drunkard person can go not just left and right, but also up and down, because there are these hoppers, random hoppers. You can maybe in 1,000 years, maybe if humans don't kill each other off already. Anyway, so yeah, you should understand these constructions for that simulation as well. Okay, so what I'm doing here is that I just integrate x against the density now, the probability density function, lowercase f of x. And I only need to worry about x going from 0 to 1, because outside, for the uniform random variable, outside the unit interval, the density is 0, so 0 times whatever is 0, so I only have to worry about this definite integral, where the density is actually non-negative, positive. Okay. Yeah, that's just some very mechanical calculus. So now we say that the mean is half, and the expectation of this of x squared is just 1/3, right? And now variance is just expectation x squared minus expectation of x the whole squared. So this is 1/3 minus 1/2 squared, which is 1/12. So, and with things like this, it's a bit boring, but generally now we sort of already getting into the world of finance, right? I mean, this is not finance, it's motivation. So, you're usually in finance, what are you doing? You're playing games based on lots of measurements, and people want to make money, right? So, and usually you'll have some notion of reward, and so you're interested in your winnings on average, right? So formally you'll have this random variable y, which is your reward, which will be some reward function. That function itself will be deterministic, r, but it will be a function of the random variable x, which could be a whole vector, or in this case it's higher dimensions even. It could be a whole vector of stock prices and so on. And current financial engineering guys like was it sabbatical at Cornell a couple of years ago, I mean, it's pretty amazing. So when I was, taking some seminars in finance, grad student, what was it, 2004 or 3 to 4, it was sort of mostly in numerics, but like a few years ago, these guys are now like processing like huge amounts of interactive, social media information and all sorts of stuff. So what's going into the input for finance is like really interesting these days. So no matter what what you have, you basically will have some kind of integral like this. And this is just Riemann and Lebesgue integral, right? There are other integrals called Ito integrals and Malavian calculus. Things get very hairy. I don't know too much about it. But so then so that's essentially expectations. So what you should realize is that probability is actually an expectation, right? That is basic understanding now. Because if you take the indicator function of the event A, right, then you have, if that's your reward function, let's say, then essentially if x is continuous, then the expectation of the indicator function of A for the random variable is just integrating over A, which is the probability that x is in A, which is P of A. So probability is actually just the expectation of the indicator function of the event. It's probability we're talking about, right? Okay. So let's do some simulations. So again, we'll do this black box for now. So uniform 0, 1 is just going to give me samples. If you evaluate it again, you'll get a different number, right? So there's some mechanism under the hood that's serving me these samples that are mimicking independent samples from the fundamental random variable uniform 0, 1. So now let's do a little bit more, right? Remember we said that probability was motivated by this notion of relative frequencies, the limits of relative frequencies approaching this thing called probability, right? So we're going to do a simulation experiment to see if this makes sense. So here is a variable to count observations of interest. So initially 0 observations, and then this is just a variable that tells us how many observations we're going to simulate. So we'll simulate 1,000. This is basically the variable for telling us which observation is going to be of interest. So for me, it's 0.5. And then I just have a for loop, right? So for I in the range of the number of observations, so this is going to loop 1,000 times. And then inside I have a conditional. If the uniform 0, 1 random variable is going to be less than the observation of interest, right? So how many times is it less than or equal to 0.5? And then I'm just going to keep counting how many things has happened. For the observation of interest. So then we just can print this. So what we've done is in these 1,000 simulations, the relative frequency of x is less than or equal to 0.5 was actually 0.505. So it seems like it's very close to what it should be, right? So if you keep increasing this number, maybe just a bit more, I don't know, it'll converge more and closer to. So this is going to be pretty pathetic, just 10, right? So anyway, so yeah, it makes sense. I think the simulation makes sense. So we can do the same with the Bernoulli half random variable, right? And the way to do this in a black box way is rand int, right? Rand int 0, 1 gives us a random integer between 0 and 1 inclusive of 0 and 1. So if I try it again, I get 1. So that's like my fair coin toss again. So once again, we can play the same game, and yeah, I can see that this is close to half. Okay, so the next random variable is called de Moivre random variable. So this is essentially the equidistributed de Moivre random variable. So there are k outcomes, so you can think of this as the generalization of a fair coin toss, but now you can mechanically think of it as a polygon with k sides. It's a regular polygon with k sides. And you can sort of imagine rolling it on the floor and then looking at the side that comes up touching the ground. And a roulette wheel with k pins, k plus 1 pins. K pins. Yeah?
I had a question about the ones before.
Yeah.
Why is it that when we're using the ints, that it's more exact?
Well, I don't know. Okay, look, I put digits 3 here, right? So let's just, I don't know. I don't think it shouldn't be more exact, right? It's just a simulation, right? So if you try it again, it'll be a different number,
Yeah, but like for me, in most of the cases, when I use uniform, it seems to be like a larger error.
Well, okay, we are going to study linear congruential generators, modular arithmetic. We will take the random number generation apart by arithmetic. I don't know how many times you tried. I mean, there shouldn't be any difference, right? Because
there should be some difference, right? You have a slower convergence in the. But I would expect the discrete one to be slightly slower. So.
Well, it really depends what's the pseudo-random number under the hood. Is it the same one or not for the two? And I'm assuming
no, of course. Yeah, but yeah.
I mean, I don't understand why you think. I think it's if it's the same random number. Okay, let's get into this later because right now we're just bullshitting, right? Well, okay.
Keep the question until the break.
Yeah. The point is, I don't think. Your observation of how many, maybe you should try 1,000 times. I mean, we don't know. So yeah, let's just use it as a black box for now, right? And okay, let's quickly get to the de Moivre before Ika. So this is essentially, it has k faces, each face has probability 1 over k, right? And this is kind of how we model this, lotto balls in New Zealand, right? It has one sorry, the balls are labeled 1 through 40. Any one of them can come out. So that's how we would model that random variable. So in general, the probability mass function, because it's discrete for this random variable, is f of x. And once again, I have a semicolon, and after that, I have this vector of parameters. Okay, in this case, I can just put k, but I explicitly lose 1 over k, because later on, we will generalize it to these values just being arbitrary. So it's 0 if x is not one of these values, 1, 2, 3 up to k, because that's how I'm painting my dice. And it's 1 over k if x is one of these values. That's all it is. And the expectation, you just march through the sum, and it's just k plus 1 over 2. And the expectation of x squared, marching again, is 2k squared plus 3k plus 1 over 6. And then the variance is k squared minus 1 over 12. So, and then this is how you would simulate it. Just rand int 1 to 40 to simulate a draw. So, yeah. So in the last minute, let's just quickly do a list comprehension. $1,000, and then if okay, I'm going to just do a for loop. My list dot and int, right? So this will give me a list that's 1,000 long, and then yeah. So I'm trying to remember for x in my list. Is this how, if I want to grab the balls that are only 10, is this how I would do the list comprehension? No, it's syntax.
You need to do x for x. So just add an x at the beginning. That right before the 4?
Yeah.
Just add an
Oh,
x.
yeah, sorry. Good. Yeah. Okay. X for x in my list. If x, thanks. Okay, so that gives me my list of the number of tens, right? So if I do length of 10, so I'm getting 37. So what I roughly expect is 40, right? So if I do 1,000 divided by 40, I should get roughly 25. Right? Yeah, so I should get 1 over 40, 0.025. So yeah, so if I do this, so divide by n. So let's say I create something called nn, which is 10,000. And okay, so I may have to do RR. Okay, so it's close to 0.255. You see what I'm trying to do? Just asking if the ball is 10. And if you change this to some other number like 20, it should also be close, right? So they should all be roughly the same. Okay, so let's have a fika break. I think I haven't ordered any coffee, so we will just, those with the cards can spot those who don't have the cards.
Whenever you have things that are more when you have things that are more regular, something that is sort of nice.